This the light that's gonna illuminate the way we moving. Trust in me, we going God mode, the theory's proven. Light 'em up, beam me up, the only GOAT, the genius one. They switching sides, I seen it coming. The plot twist, a convenient one.
What's up guys, it's your boy Quantum Pinguino, and today we're going to be discussing something called the Strangelet Catastrophe. We're going to jump right in and get some historical context on what a strangelet is and why people were worried about it. In 1971, while at sabbatical at Oxford University, researcher Arnold Balmer proposed the concept of collapsed nuclei. To understand the concept of a collapsed nucleus, let's use a toy example of lithium-3. Although this atom does not occur naturally, it simplifies some of our math later on. In our example, a collapsed nucleus occurs when the 3 protons inside the lithium-3 atom all collapse into a much smaller radius. Let's take this radius to just be the radius of a single proton. Balmer proposed that this configuration was actually more stable than the original unbound state of the lithium-3 nucleus. To help visualize this, I made this plot of the potential as a function of the radius of the nucleus for the lithium-3 atom. But please note, this is not the scale. So if you look on this plot, we have 2 relative minima, one at the radius of the lithium-3 atom and one at the radius of the collapsed nucleus. To get from the radius of the nominal lithium-3 atom on the right to the collapsed radius, you have to overcome this potential barrier. So now we're about to get a bit mathematical, so those that aren't too familiar or comfortable with mathematics, just look at the numbers that I'm boxing, as that's the important part. We can use the WKB approximation to find the probability that we can tunnel through this potential barrier. Taking the number of baryons A to be equal to 3, and then computing the integral using some hand-wavy approximations, we get that the probability of tunneling is e to the negative 18. This may seem extremely low, but we also have to take into account the number of times that we attempt to tunnel. We can approximate the number of attempts at tunneling using something called nuclear compressibility, and we'll use the physicist's best friend, a simple harmonic oscillator. Without going into too much detail, K is the nuclear compressibility, and R0 is the standard nuclear radius, and A is the number of baryons. We can use this to obtain the frequency of 10 to the 22 attempts at tunneling per second. And now that we have both a probability and a frequency, we can multiply both of them together to find the average amount of time needed for us to have one tunneling event, which turns out to be 1 femtosecond, actually a very short amount of time. And this is exactly what Balmer concluded, that at low nuclear numbers, this would happen extremely quickly, but it cannot be the case since we, for example, have helium-3 atoms still in the universe. Now I don't do the math here, but for gold, which has A equals to 197, the amount of time that it would take to have a tunneling event is over the age of the universe. However, Balmer coined this Goldilocks region between A equals 16 and A equals 40, where these tunneling events have a non-trivial chance of occurring, aka they don't take over the age of the universe, and it could lead to some of these collapsed nuclei that we just have not yet observed. This sets the stage for Witten's proposal in 1984. However, before we get to that point, there's a whole decade of discoveries that we have to go into, specifically a little thing called the discovery of QCD. To understand QCD, let's first look at the more familiar QED, or quantum electrodynamics. On the plot on the left, the x-axis represents Q, the momentum scale, which is inversely proportional to the radius via the Heisenberg uncertainty principle. The y-axis represents the strength of the QED coupling, and if you look around the low energy regime, which means high distances, you see the familiar fine structure constant, 1/137. As you go higher in energy, or lower in distance, we see that the coupling constant becomes larger and larger. In English, what this is saying to us is that if you had a pair of, let's say, an electron and a positron, then at small distances, the coupling strength between them, or attraction, is very large, while at larger distances, it's very small. This is exactly the opposite of what we see in QCD, or the strong nuclear force, the interaction that binds quarks together. At large distances, or low energies on the plot, we see that the coupling constant grows and diverges as we keep going larger in distance. This is a phenomenon called confinement, or in English, the fact that quarks don't like being alone, and they like being in bound states with other quarks. However, when you go to small distances, or high energy, we see a phenomenon called asymptotic freedom, where quarks actually behave like free particles once they enter these bound states and are very close to other quarks. The observation of this inverse behavior in QCD relative to QED is what won these 3 scientists the Nobel Prize in 2004. The discovery of QCD also directly leads into the next topic we will discuss in this video, called the MIT bag model, which is a toy model for confinement of quarks. The MIT bag model describes the balance between two forces, the first being the energetic cost of confining quarks in a bag of radius r, shown by the equation E bag equals B, the bag constant, times the volume of the bag, 4/3 pi r cubed. The second force pushing outwards comes from the kinetic energy of all the quarks inside the bag. We can find the total kinetic energy by summing over all the quark flavors and all their spins inside the bag. The quark eigenstates are defined using these k and m values. K is inversely proportional to the radius and comes from the spherical Bessel functions, while on the other hand m is simply the mass that comes from the flavor of the quark itself. So when you derive the total energy of the system with respect to r, you can then find the value of r which minimizes the energy and gives the system the most balance, and this is called the equilibrium radius of the bag. After QCD was discovered, this is the first toy model that describes how quarks behaved when confined into a bound state such as baryons or mesons. The last piece of the puzzle comes from the estimation of the strange quark mass by the duo of Gasser and Leutwiler, who are both now Professor Emeritus at Bern University. Now the next section is going to be pretty math heavy, and I want you guys to bear with me. It's not that bad, it's just a lot of fancy symbols and words, but the math is pretty straightforward. But I still know some of you are going to be acting like this next clip. So, time to lock in. Let's first talk about pions and kaons. These particles were both discovered a few decades before this paper was published, back in the 50s, via cosmic ray observations. Pions are composed of a combination of up and down quarks, while kaons are one strange quark followed by one either up or down quark. This is exactly what QCD predicts with the fact that quarks like to be confined in bound states. Now, arguments from chiral symmetry tell us that the square of the mass of each either the pion or the kaon is proportional to the sum of the mass of the constituent quarks. Now, this is where the algebra 1 comes in. We can set up a proportion taking the ratio of the square of the kaon mass over the square of the pion mass and eliminate this b naught constant that we don't know. At this point in time, we know the mass of the kaon and the mass of the pion pretty well, with some level of uncertainty that's obviously much larger than what we have in the present day. In these equations, the m hat represents the average mass of the up and down quark. And what we do now is that we simply solve for the ratio of the strange mass to the average mass of the up and down quark. And since this can be expressed purely in terms of the mass of the kaon and the mass of the pion, we get a ratio of about 20 to 25. The conclusion of all this is that before any experimental measurement was made of the strange mass, we actually had some kind of estimate of it being 100 to 125 MeV. This is very close to the modern day experimentally constrained measurement of the strange mass of 93.5 MeV. Now, as if he was Thanos after collecting all his Infinity Stones, famous theoretical physicist Edward Witten is going to drop a bomb on the physics community when he publishes Cosmic Separation of Phases. He puts together all the things we've been discussing in this video: Bodmer's proposed idea of collapsed nuclei, the discovery of QCD leading to the MIT bag model, and the strange mass being estimated around 100 MeV. I'll spare you guys from the math, but what Edward Witten does in English is that he uses the MIT bag model in the limit where we have an infinite Fermi sea of up, down, and strange quarks. He then uses the value of the bag constant commonly used at this time and the estimated strange mass in his calculations to conclude that the energy per nucleon in this Fermi sea is less than 930 MeV. But what the heck is the significance of 930 MeV? To understand this, we have to have a crash course on what the heck is a star. A star does something called nuclear fusion, which we can think of as just a very long game of 2048. The sun continues to collide these atomic nuclei until you get heavier and heavier atoms with more protons and neutrons in the nucleus. For lighter atomic nuclei, this process actually releases energy, which is why the sun is always shining and so bright in the sky. The win condition, or some may say the lose condition, as this is when the sun starts losing its fuel, is when the sun fuses iron-56. Fusing past iron-56 costs the sun energy, which it does not want to do. Jumping back to Edward Witten's conclusion, if this bulk strange matter, an analog for Bodmer's collapsed nucleus, has lower energy per nucleon than iron-56, then it's possible that this strange matter is actually more stable than iron-56, and you could have strange stars which have nuclei of strange matter. The creation of a single instance of strange matter could trigger an apocalyptic scenario where it converts ordinary nuclei into strange matter and devours everything in its path. These kinds of pseudo-apocalyptic scenarios had many people worried and led to these kinds of papers being released in the late 1900s, early 2000s, where people were worried that if we built particle colliders, we could produce this kind of strange matter that could end the world. And this is where we'll end part 1. In part 2, we'll go into more depth on these papers, so I thank you all for watching, and I hope you all have a great day.